Our next speaker that will be also speaking about like group type of analysis and especially speaking about insaturation is the one and only Petr Vozka from California State University in LA that will be speaking about counting double bonds, GCxGC-FID for plastic pyrolysis. When you are ready, Peter, take your time.
Thank you, Paige, for the kind introduction. Let me do it this way. I don't want to turn around, so I'll use this laser. So, good morning, everyone. It's been 3 years since I've been having a presentation here, I think. Last year, our two groups were upset that I didn't talk about the olefins. Then we had a phone call, Zoom call, and they are not here today. So, are there still any fuel people in the audience? Okay, so you will have to bear through this presentation. So, a lot of these things you heard before. I mean, the plastic recycling is in trouble. Dr. Thoraman talked yesterday about how and where the plastic waste goes. So most of it is still, unfortunately, landfilled. We don't recycle much. A lot of you seen those terrible pictures of the ocean polluted with plastic waste. That's only 3% of kind of the total plastic waste. So you can imagine how much of these plastic waste or where does it end and how terrible it must look like. So I've been kind of blessed because I was able to work with a lot of universities and with some kind of industry companies, and they kind of wanted to do something with this plastic waste. So we decided we're going to help them. So it's, all the universities that you see on the screen, some of the other ones that we just started a collaboration with. But basically, they do the cool job. They kind of take the plastic waste. They usually create something useful. And then they send us that something, and they want to see what's inside. So that's what we do. They use different real plastic kind of feedstock, plastic waste feedstock. So it's not like just virgin polymers. They start with virgin polymers, then they really kind of shift to the real plastic waste. And so because of this, we were kind of able to publish some papers looking into kind of the depolymerization pathways, what's happening in these different processes, if it's catalytical, non-catalytical, and so on. And most of the time, we kind of develop these, reaction pathways. And most of the time, you can think about it, right? And you've seen it yesterday in some of the presentations. If you break the polymer, you're going to get a lot of olefins, a lot of alkenes. And the problem is that currently, I guess you know what olefins are. So the problem with these products, with these fuels-like products, is that it's not just one type of kind of olefins. It's kind of all over the place. So if you imagine, your chromatograms, if you work with hydrocarbons, the olefins are basically just all over the place. So the big question is, and I've seen some of these kind of olefin methods that are available. But the question is, how can we quantify these olefins in complex samples, but as detailed as possible, not just kind of the total numbers. And so what we did first or not first, it took like 3 years. Some of you might be actually the reviewers of this paper, so I apologize. I think it's like 35 pages. But we look into all the possible methods that are there to quantify olefins in kind of plastic waste fuels or in fuels in general. And because it's kind of heavy to digest, we also published this paper with interactive PowerPoint presentation where we kind of summarize all these methods. You can click, let's say for bromine number we just heard. So you can click on bromine number. You can get some very, I would say, digestible information very quickly before you then jump into the paper and read it. So this would be like bromine number. You can then click, for instance, on GCxGC, so you can see what the GCxGC can do. And you can also kind of see what the results are in that method. So those who are not familiar with bromine number, kind of the way this method reports the results are not perfect. You're getting some kind of weird units, like grams of bromine per 100 gram of samples. It really doesn't tell you much regarding the olefins. So we were kind of thinking, what else can we do? Because most of these methods kind of report only the total olefin content. And as I just said, it's not kind of ideal results because you're getting these milligrams of bromine. I mean, many of you know these methods. Another problem is with Haley actually mentioned Tuesday. So what we discovered, like doing during our other papers we published, that FIA, for instance, reports some dienes as heteroatomic compounds and heteroatomic compounds as aromatics. So these methods basically kind of fail when they have to analyze kind of the plastic waste. The reason is what I didn't mention, that you might have up to 58% of olefins in your feed, which this is not what you're going to get from the crude oil. So the question is basically, what can we do to kind of quantify but detailed kind of olefin content? So there are kind of 2 ways that we exploring, and we publish some of the studies I want to kind of talk about and give you update about the one that we're working on currently. So we combine, obviously that's why I'm here, GC by GC with derivatizations and with adsorptions. So the combination with adsorptions, I'll discuss first, but just to give you kind of like I need to put some chromatograms in the slide. So this is commercial diesel on the left side, and on the right side, this is kind of like high thermal processing diesel fuel-like sample, so you can see how complex these samples are. This would be a diesel fuel kind of from pyrolysis oil after hydrotreating, so you can see, it's a lot of compounds. So one-dimensional GC would kind of fail here. So the first question is like, where do these alkanes kind of elute? So this is a reverse phase. You can probably guess. Those who not working with the reverse phase, so your N-alkanes are up here. Anything above, isoalkanes, below cyclo, and then you have your aromatic region. So what I didn't mention is we're using GCxGC-FID for these projects because it's very quantitative and very useful for hydrocarbons. So we have to draw this classification. My students, they always love drawing this and kind of validating it. It is a very quick process. So if you need any tips, just let me know. But what we discovered running, all the standards, some compounds we synthesized. So what actually has been taught in the kind of literature, if you go through the literature, so people thought since, alkenes are basically very similar to cycloalkanes, so they elute in only that region. That's actually not true. So, where your isoalkanes elute, we have isoalkenes there. In monocycloalkenes region, we have olefins with one double bond and linear olefins, and so on and so on. In dicycloalkenes, we have olefins with 2 double bonds. In tricycloalkenes region, olefins with 3 double bonds. So you can see that there is a trend. And then aromatics is kind of copy-paste. So we said, what can we do, kind of, combining these 2 kind of methods. So the first one was the GCxGC we combined with adsorption. So we published a paper, it was this year, a few months ago. So we used silica, silver, silica cartridge. I'll show you in a little bit. This is a very simple method. You just push out a sample through the cartridge, you run it before and after, and you do chromatogram subtraction. But kind of the thing that I won't please you, because usually people at least believe, my N-alkanes are safe. It's just, one standing compound. So that's at least we have like this group we kind of have safe. But unfortunately, that's not true, because if you have for instance, a polypropylene-rich kind of feed, then you have a lot of kind of coeluting compounds with even N-alkanes. So what I'm showing here, for instance, is if you would look at your N-alkanes as they are, and if you would quantify them, you would get these numbers. But if you then do the method that I'm going to discuss in a little bit, and you actually remove your olefins from that region, you can see some like drastic changes. So even like what might happen is that people over-reporting N-alkanes, even N-alkanes. So how does this method work? Is very simple. We have a kind of SP column. The upper part is very simple. The bottom part is a little bit advanced because we're cooling the vials in case you're working with like low boiling point products like gasoline or even something lighter. And basically the method relies on monitoring area losses in the respective groups, and kind of the loading is around 1.5 grams. The particle size is mentioned here. We tested multiple loadings, multiple different particle sizes, so this is kind of the optimal conditions. You only need 50 microliters of the sample. and it takes about 15 minutes to separate. Now, what's happening once you kind of push your sample through or you let your sample go through, we look at the peak area difference. What it means, we run the sample as is, then we kind of push the sample through the cartridge, we run it for the second time, and because it's FID, we're getting the weight percent for all of these groups you've seen. So the difference in the weight percent is basically your olefin content. And whatever kind of stays there is your real cycloalkane or isoalkane content. This is kind of precise and accurate results, but it starts being precise and accurate about like 5 weight percent, which is not bad because a lot of these plastic waste fuels, they really have huge concentrations. And so far, I think is the most kind of cost-effective approach for the olefin content if you really want to get details. The second thing we work on are the derivatizations. I think you might have seen some of these things before. So this is what happened. This is how we started doing it, and I'm going to tell you how we hopefully improve it. So we basically take the sample, we put internal standard DMDS, dimethyl disulfide, and iodine solution. We put it to the oven at 70 degrees Celsius for at least an hour. Then we treat it with sodium thiosulfate to stop the reaction. And then we analyze the organic phase. We always analyze, again, the sample as is, and then the sample after this derivatization treatment. Theoretically, what's happening is in your reverse phase, if this is kind of your alkene pre-derivatization, if you derivatize your alkene, it became more heavier and more polar, so you basically shift that peak somewhere else. That somewhere else space is important. I'm going to talk about it in a little bit. But with DMDS, if you imagine the molecule, it's not that heavy, so we had to kind of do some improvements. This is not new. This is not something we discovered. I think this is from paper from like 1870 something. So we said, let's do that. Let's test it. So we did it. This is kind of how 3D look like. So you can see kind of some results here. This is a jet fuel boiling point kind of range fuel. You can see some like differences, like these peaks, disappearing because we derivatize them and move them somewhere else. These would be alpha olefins kind of being derivatized, so you can see the peaks kind of really nicely shift. This ugly blob, that's your DMDS, and then DMDS polymers. That's one of the limitations I'm going to talk about in a little bit. But what that allows us to do is to kind of look at whatever, people report or how you would normally like kind of report your samples. And we can break these groups into whatever really the, saturated hydrocarbons are versus your kind of alkenes and so on. This method doesn't work for olefins. I mean, it does. We don't report olefinic, aromatic olefins, because the peaks are moving actually to that aromatic region. So that's one of the limitations I'm going to discuss in a little bit. But it works kind of for the aliphatic olefins, which might be sometimes useful enough, depends on your feedstock. But not just that we can do these totals, because I told you at the beginning we really want to get to details. So we can actually go all the way to carbon numbers. So this is, for instance, the monocycloalkane region. So if you look at, carbon 6 or compounds with 6 carbons, so what appear to be 9.27 weight percent, we can actually break into whatever the olefin is with 6 carbons and 1 double bond, and whatever the monocycloalkanes really are. We validated the method with, we did bromine number, we tried to then GCxGC results to recalculate using average molecular weight to, the olefin content and so on. But some of these methods still fail. So what we also do, we kind of take fuel that is fully hydrotreated, so we know there are no olefins, and then we spike it with kind of olefin mixture and so on. So we're preparing this paper, should be hopefully published soon, within like 2 to 3 years. As I didn't mention, but I only have undergraduate student and master student, so sometimes it takes some time. But I want to discuss some of the drawbacks and then what we kind of took from those and where can we kind of move. So some of the drawbacks of the method. So the adsorption is, as I said, precise and accurate, only above kind of 5 weight percent, which might or might not be a drawback. And it only works for aliphatic olefins and alkyl benzenes and alkenyl substituted alkyl benzenes. So if you have anything heavier, it doesn't go through the cartridge. If you actually think about it, because I know there might be questions, what about the TOF-MS? Can we like figure out what these compounds are? Yes, you can. You can then elute, of course, your trapped fraction, and you can run that through TOF-MS, or in the derivatization step might be even easier, because you would have your two sulfur metal groups, and then you can analyze those using TOF-MS and kind of back calculate the results. I think Dr. Sinovek group, they did it. But as you know, TOF-MS and quantitation is not the easiest part. For the DMDS, the first shock for me was that it took me 6 months to get iodine in California, because it's DEA regulated and at many places as well. DMDS is kind of smelly. That's not a huge problem. 70 degrees Celsius might be challenging for like lighter or low boiling point compounds. We had no problem with gasoline-like samples, but I guess the lighter ones could be a problem. And then only works for aliphatic olefins. So again, if you need to analyze your aromatic olefins, that would be an issue. But the main problem is that if you have heavier samples, I mean like diesel-like samples, then the DMDS is not heavy and polar enough to shift to the aromatic region. What does that mean? So if you look into this region, which is like a tricyclo alkene region, you can see that if we, like these alkenes, they don't shift all the way to the aromatic region, but only there. And some peaks might be moving from there, so the calculation will be kind of very complicated. So we kind of talked about some potential solutions. So one of them is to kind of replace iodine with something different. Iodine only initiate the reaction, so maybe having some photo, initiator, things like that. DMDS, since it's not heavy enough, so we tested heavier disulfides. I'm going to show you in a little bit. And then ideally, if you can move from 70 degrees Celsius to room temperature, it will be ideal. And having heavier disulfides would also save the main problem for these like heavier like fuels. So we tested multiple different disulfides. I'm not showing all of them because the winner, we don't want to reveal yet. We're working on some like patents and publications. So, but we tested these and one more. We tested multiple conditions. You know how it is: temperatures, time, solvents, ratio of the derivatization agent versus the solvent and sample, and so on. Here are some results. So some of these disulfides perform better, some worse. If you think about dibenzyl, it's really bulky molecule, so it doesn't always get where it needs to. Other complexes, but we also had like a lot of successful kind of attempts. The question is, if we find the disulfide that would kind of work and do the job. So of course we did. I wouldn't be presenting if we didn't. So the way actually you can figure it out if your sample is really fully derivatized is we're using 1H NMR. I know this is spectroscopy, so hope I'm not going to offend anyone. But in the spectroscopy, you have this kind of bands where you can see your double bonds. So this would be your kind of alkene protons. So this is pre-derivatized sample. Once we applied our method, you can see that these bonds are gone. So we're getting like a full derivatization. And the cool thing is it works at room temperature, and you don't need iodine. Well, sorry, we still use iodine. We're working now on updating and see if we can trigger the reaction without the iodine. So just to kind of summarize this, so the previous kind of work, we proved that if we're using DMDS and 70 degrees Celsius, should not say 24 hours, but 1 hour, it works for gasoline samples. However, this is not useful for heavier like jet and diesel fuel samples. So currently we we find a molecule that works for us. We still need to work on the validation, and then we also want to run the samples through TOF-MS. And absolutely ideal would be having GCxGC with TOF-MS and split to VUV probably, because that could help us a lot. So that would be pretty cool. We don't have that capability yet. I think that's all for me. I want to thank all the sponsors who helped me to equip the lab. Many of you sponsoring this event, so thank you very much. And as I mentioned, this work has been done by only undergraduate and master students, so I'm very proud of them, because it's not easy, doing this type of work, a few undergraduate students. Thank you very much. If you have any questions, I'm very happy to answer those.